Imagine you're treading water somewhere in the Southern Ocean, just south of the Antarctic convergence zone. The water around you is just barely above freezing. There's almost no light. And then you make the mistake of looking down. What you'd see beneath you is not what you'd expect from one of the most hostile environments on Earth. You wouldn't see emptiness. You'd see spiders with leg spans wider than your arm span crawling across the seafloor below. You'd see jellyfish trailing tentacles longer than a blue whale drifting past you in slow motion. You'd see squid the size of sedans moving through the dark, slowly, without any apparent urgency, because nothing down there is large enough to threaten them. Every single one of these animals has a much smaller relative living in warmer water somewhere. The spider is the size of your thumbnail in a tropical reef. The jellyfish is dinner plate-sized in the North Atlantic. The squid is a glass squid, nearly transparent, barely a foot long, off the coast of Japan. But here in the Antarctic, the cold did something to them. And the reason it happened is not what you'd guess. It's not predation pressure. It's not food abundance. It's not isolation. It's the water itself. Specifically, what cold water holds that warm water can't. And once you understand the mechanism, the giants stop being surprising. They start being inevitable. Cold water holds more dissolved oxygen than warm water. This is basic chemistry. Gas solubility increases as temperature drops. But the biological consequences of this fact in the Southern Ocean are anything but basic. For cold-blooded marine animals, creatures that absorb oxygen directly from the water through gills, skin, or specialized structures. The oxygen content of the water is the single most important constraint on how large they can grow. More oxygen in the water means more oxygen available to cells. More oxygen to cells means larger bodies are metabolically sustainable. In warm tropical water, oxygen dissolves poorly. The animals that live there are effectively capped by the oxygen ceiling the water imposes. They can only grow so large before their cells can't get enough. In the Antarctic, that ceiling is gone. The water here is so cold and so oxygen-rich that for cold-blooded animals, the usual size constraint simply doesn't apply in the same way. Evolution, presented with an environment where the physiological brake on growth has been removed, did what evolution does when constraints disappear. It pushed. Over millions of generations, animals that happened to grow slightly larger survived slightly better. Better insulation, better heat retention, better energy storage across the long Antarctic winter. And that slight advantage compounded, generation after generation, until the animals we find here today are barely recognizable as the same species as their warm water relatives. This is polar gigantism, and the Antarctic is where it runs fullest. The most extreme example is also the one that most people misfile under a different category. The colossal squid, Mesonychoteuthis hamiltoni, is the largest invertebrate on Earth by mass. It can exceed 1,000 pounds. It has eyes the size of dinner plates, the largest of any animal alive, which exist to gather the faint traces of bioluminescent light in the deep Antarctic water. It has hooks on its tentacles, not suckers, hooks, that rotate independently, capable of locking into prey with a grip that doesn't release. Most people, when they picture a giant squid, are picturing the colossal squid. They're different animals. The giant squid is longer, but lighter, found globally in deep water, and shaped like what a squid is supposed to look like. The colossal squid is a different thing entirely. Massively built like a tank rather than a torpedo, shaped by two simultaneous forces that stacked on top of each other to produce something genuinely unlike anything else in the ocean. Because the colossal squid lives both in Antarctic water and in deep water, it experiences polar gigantism from the cold and a separate phenomenon called deep-sea gigantism from the depth, where the same logic of oxygen availability and reduced predation pressure produces similar results in a different context. Two separate evolutionary pressures, both pointing in the same direction, acting on the same animal at the same time. The result is the colossal squid, double gigantism, the largest invertebrate that has ever existed. We have never seen a live adult in the wild. Every specimen we've examined came up in a trawl net, already dead, usually badly damaged by the pressure change on the way up. We know its maximum size from carcasses found in the stomachs of sperm whales, which swallow them whole and whose stomachs preserve the beaks intact. From beak size, we can estimate body size. The numbers we've arrived at suggest we may not have found the largest ones yet, but the squid, at least, is an animal most people have heard of. The sea spider is harder to prepare for. In a tropical reef, sea spiders, technically pycnogonids, not true spiders, are about the size of your fingernail. Delicate, almost invisible, they move across coral in the peripheral vision of everything around them, small enough to be irrelevant. You could look directly at one and not notice it. In the Antarctic, the same family of animal reaches a leg span of 70 centimeters, just under 2.5 feet across. They move across the seafloor on legs that function as stilts, stepping over sponges and sea urchins. They breathe through those legs. Their leg segments are hollow, and oxygen diffuses directly through the leg walls into the circulatory system. More oxygen in the water, more leg surface area, more body it can support. The Antarctic sea spider grew so large because the legs that breathe for it became so efficient in cold, oxygen-rich water that the usual respiratory bottleneck simply wasn't there. What do they do with all that size? They hunt. They use a long, tube-like proboscis to pierce soft-bodied animals like sea anemones and siphonophores, then extract the soft tissue by suction. At their size, the things they hunt are also Antarctic scale. The sea urchins they prey on are themselves larger than their warm water counterparts. The sponges they move through are centuries old, growing slowly in the stable cold, reaching sizes that would be impossible in warmer ecosystems where metabolic activity would erode them faster. The Antarctic seafloor, if you could walk across it, would feel like a forest left to grow undisturbed for geological time. Old, massive, slow, and completely unlike anything at comparable depths elsewhere. Then there's the lion's mane jellyfish, Cyanea capillata, the longest animal on Earth. A blue jellyfish, same genus, warmer water, reaches about 50 centimeters across. The lion's mane, in cold northern and southern waters, has been documented with a bell diameter of 2.3 meters and tentacles stretching 37 meters. For reference, a blue whale, the largest animal alive, reaches about 30 meters in length. The lion's mane jellyfish, at maximum recorded size, is longer. It achieves this without a brain, without a skeleton, without a heart, and without anything most people would consider a sensory system beyond basic light detection. It is, at its core, a radially symmetrical bag of water and protein, trailing nematocyst-loaded tentacles through the water column to catch whatever drifts through them. It is extraordinarily simple. And in the Antarctic, where the oxygen ceiling is removed and the cold slows everything down to a crawl, it grows to a size that is, objectively, absurd. The tentacles aren't just long. Each one is lined with millions of individual stinging cells, nematocysts, that fire on contact, independent of any central nervous input. A jellyfish that has been dead for hours still has active nematocysts on detached tentacles. Size doesn't make the lion's mane more dangerous in the way a larger predator is more dangerous. It makes it a larger net. A 37-meter net, drifting through water with no visibility. Most things that drift into it don't drift out. What ties all of these animals together, the colossal squid, the sea spider, the lion's mane, is something beyond just their size. It's what their size costs them. Polar gigantism is metabolically cheap in the Antarctic, specifically because everything there is slow. Cold slows metabolic rate. Chemical reactions that drive cellular processes run slower at lower temperatures. An Antarctic starfish, Also larger than its warm water relatives, sometimes with more than 50 arms, where a tropical starfish has 5, lives for 40 to 50 years. Its tropical equivalent lives 5 years. The Antarctic version grows slowly, reproduces slowly, and dies slowly. But it also burns energy slowly enough that its enormous body remains sustainable. This creates a second-order effect that is stranger than the gigantism itself. When metabolism slows, generations lengthen. When generations lengthen, evolution slows. The Antarctic has remained cold and stable for approximately 35 million years, since the formation of the Antarctic circumpolar current isolated the continent thermally from the rest of the world's oceans. In that time, the animals that lived there didn't need to change much, because the environment didn't change much. They optimized once, deeply, for conditions that then held steady for geological time. The result is that many Antarctic animals are, in the most literal sense, living fossils. Sea spider lineages found in Antarctic sediment cores from 30 million years ago are morphologically almost identical to what's crawling on the seafloor today. Some Antarctic fish have blood chemistry, specifically antifreeze glycoproteins that prevent ice crystal formation in their cells, that evolved approximately 20 million years ago and hasn't meaningfully changed since. They are solutions to a problem that stopped changing, and so the solutions stopped needing to change too. Which brings us to the part that most discussions of polar gigantism skip over entirely. Everything that makes these animals extraordinary also makes them catastrophically fragile. Polar gigantism works because cold water holds more oxygen. Warming water holds less. A colossal squid perfectly calibrated for 1.8 degrees Celsius water faces a different physiological reality at 0 degrees Celsius, a different one again at 1 degree C. Its size, its metabolic rate, its oxygen requirements, all of these were optimized for conditions that are no longer stable. Studies on Antarctic sea spiders have already found that in regions where water temperature has risen by measurable fractions of a degree, maximum body sizes are declining. The animals are still there. But the largest ones, the ones that polar gigantism spent millions of years producing, are getting smaller. The oxygen ceiling that polar gigantism removed is being reinstalled, fraction of a degree by fraction of a degree. For animals with 40-year lifespans and generational timescales measured in decades, the rate of environmental change happening now is not something they can adapt to. Evolution that took 35 million years of stability to produce cannot respond in a century. What polar gigantism built, slowly and patiently, in the most stable cold water on Earth, is now losing the condition that made it possible. The colossal squid exists because the Antarctic stayed the same for longer than most ecosystems stay anything. It is a product of deep time and extreme stability, and it is one of the most complete expressions of what evolution can produce when given enough of both. The ocean is getting warmer at rates not seen since before the Antarctic circumpolar current existed. There is no version of that story where the giants survive unchanged.